Good afternoon, everyone. Thanks for being here today. My name is An Zhang and my teammate Tirei Cho. In this presentation, we would like to talk about non-radiating photonics with resonant electric nanostructures. Before I begin, I would like to give everyone an overview of our presentation. First of all, I will give you the introduction. Then I will show you two types of them and compare the difference and the same between them. Lastly, Qirei will talk about some applications and summary. In nanoscale, photonics play an important role. In photonic research area, non-radiating source of energy has received more attention in recent years. Many remarkable studies are talking about localize the electromagnetic fields of high intensity within small volumes of matter efficiently, and we can overcome the problems of lossy by metals and plasmonic materials. So, what is non-radiating source? It means which do not emit energy in the far-field region. Non-radiating sources develop in different types. First, non-radiating state could be generated by combining classical electric. Second, magnetic dipole mode with electromagnetic toroidal multiples. One of simplest is a toroidal dipole mode oscillating out of phase with respect to a single electrodipole. We can also call it simply a dipole. Third, the complex interaction in may resonate electric structures. They can also support a different class of non-radiating state characterized by no energy leakage and specially localized profiles. We can also call it bound state in the continuum. Next, we are going to talk about quasi. It means very similar but not the same. There are four reasons lead to cycle to being incomplete: material absorption, finite size simples, structure disorder, and surface scattering. I would like to move on to types of non-radiating state of light. The term anopole means without poles, and it was originally proposed in the late 1950s by to model elementary particles that do not interact with the electromagnetic fields. The state could be created by a suitable combination of toroidal dipoles mixed with electric and magnetic multiples. As you can see, this is a picture about an apple. These two dipoles can completely cancel each other by destructive interference in the far-field region and create the standing wave. The first experimental demonstration of an apple was reported in 2050 for the electric silicon nanodisk. In this work, they confirmed the existence of spatial conditions for an anopole state in spherically symmetric structures made of materials with sufficiently high index. As this type of structure is not particularly suited for observation under plane wave illumination, they demonstrate that by optimizing the height and radius of each nanodisk, it is indeed possible to suppress high-order multiples and observe the direct interference of toroidal and electrodipoles at the spatial frequency, which can be tuned in the visible and near-infrared. Theoretical results were confirmed through scanning near-field optical microscope. Experience with 15 nanometer thick silicon nanodiscs of diameters varying from 200 to 400 nanometers. Secondly, I will talk about bound states in the continuum. Another family of non-radiating states supported by all dielectric nanostructures is so-called bound state in the continuum. These states correspond to peculiar resonance. They are localized within an radiation continuum spectrum, while having no energy decay. Next, please look at the picture, which is about different families of states sustained in an open photonic system and their position. You may be confused. What about difference between bond state and BIC? Let's look picture on the right. The upper part is conventional quantum well, and the regular bond state is below the spectral range. When we modulate the potential of quantum well with spectrally unbound oscillations, this situation allows for localization for a bond state within the continuous spectral range. That is BIC shown in blue. I'm going to mention two main approaches to realize a BIC. The first approach is symmetry protect BIC. It's the waveguide with a cavity tuned to the frequency, for which almost of one symmetry are evanescent. Under this condition, only single frequency is allowed and cannot radiate into the waveguide. The BIC condition is fulfilled when the mode frequency lies within the continuum spectrum of radiating modes. Another of BIC is accidental BIC, originating through turning of some system parameters. They can be divided in two major groups. Fabry-Perot BIC, based on two identical resonances of two interacting cavities coupled through a single radiation channel, and Free-Jack-Winton BIC, representing the interference of two different resonances in the same cavity. These conditions can be fulfilled through the turning of the parameters of two coupled resonances when identical omega-1 equal to omega-2 and gamma-1 equal to gamma-2. In this section, we analyze the relationship between anaples and BIC. First, the difference on radiation. If you want that the radiation is allowed, it can be achieved by only destructive interference of all multiples at the same time. Anapole did, but it does not happen on BIC. Second, for any photonic structures, BIC represents eigenmode of the system. However, it is not the necessary condition for observation of anaples. Third, difference on energy. In anapole, when electromagnetic energy is accumulated, it scatters, but the total electromagnetic fields outside the scatters mimic the incident field without distortion. On the contrary, since BIC proceeds in finite Q factors, they cannot couple to radiation channels and accumulate energy when excited from the far field. Next, important topic, we will introduce you some applications. A field enhancement up to several times was obtained due to excitation of the anapole state in isolated nanoparticle normally. This enhancement is guarded by the interference, which cancel each other but mutually enhance the field inside the resonator. Higher field enhancement was reported for individual slot nanodisk. The enhancement was improved by taking advantage of the high reflective index of the material by designing air holes in the nanodisk. Field enhancement in high-index dielectric metasurface with gap meta atoms at the anapole can up to several thousands. The quality vector Q vector, which governs the performance of any resonating structures. This idea is by increase the Q vector. When high Q vector approach 1 million, near field enhancements can up to 10,000 times. In BIC, we can use the same way. We can increase the Q factor by tuning the resonator parameters appropriately. Although the times of field is not mentioned in the studies, but with such a high Q factor, I think the result should be impressive.
Hi everyone, I'm Qirui Cho, and first I introduce the nonlinear harmonic generation. We want to get high Q factor and strong field enhancement. So in this part, we are aiming to enhancing the efficiency of nonlinear light-matter interaction. And I source 3 mechanism and 3 material optimization to improve. In mechanism, the first is higher order nanopores supported by larger germanium nanodisk, using the characteristic of narrow scattering cross-section and higher localized field in confinement, just like Picture A elaboration. As Picture A shows, structure composed of a large silicon nanodisk. This system is able to sustain the nanopore state. We get a result of it generates a conversion efficiency 1 order of magnitude higher than that observed for third harmonic generation at 500 nanometer. And the second is placing the silicon nanodisk on the top of gold reflector. Using the characteristic of metal has free charge oscillation at the interface. We get a result of the high THG conversion efficiency of 0.01% was expectantly achieved. Last but not least is proposing a fabrication on ion beam bearing of silent nanowire, and turn the result out that it may generate different design of arrays and lattice of nanodisk. And in material part, the first is quasi-BICS in periodic arrangement of asymmetry meta-atoms. We get a result of that it enhances the efficiency of nonlinear harmonic generation in meta-surfaces. And the second is to insert waves give rise to 4 waves. Using the characteristic of the frequency comp generation in 2 coupled resonators support BIC. We get a result of that it provides a way for all optical generation of waves with ultra-low frequency. And the last is isolated sub-wavelength ALGAS nanoparticle be given. Using the nonlinear effect and success predict a record high conversion efficiency for nanoscale resonators. As picture B and C, elaboration. Compare picture of B. We can find picture C has obvious high peak. The second, I introduce the metamaterials and metasurfaces, and my aim is to bring the unique properties of nanopores to the microscopic scale. Method we choose is to analyze toroidal dipole moment in metasurfaces at different frequency ranges. And I put 4 parts. The first is mathematical. I sought for metallic plasmonic dielectric part. In metallic, the moment losses in metallic part play the dominant role in the visible and near-infrared regions. In plasmonic, the performance of plasmonic metamaterial is not so high in radio frequency. In metasurfaces, dielectric metasurface demonstrates strong toroidal response. And the second is metasurfaces. The mechanism is inserted wave linearly polarized along the central while induced the implant toroidal moment, which is compensated by the electrical dipole moment. This comes the result of the metasurface consisting of silicon spilled nanodisk arrays demonstrated a higher Q factor and its application. Metasurfaces composed of a perforated 100 nanometer thick silicon layer, as Figure A elaboration. Figure A is composed of planar 100 nanometers thick silicon layer with cylindrical perforations. The other application is trend of dielectric disk guiding the anode excitation was shown. That such waveguides are extremely robust against physical bending and spilling, and that the anode state is efficiently transmitted through the S-shaped band waveguide and Y-shaped spiller, as Figure B elaboration. The left hand is Y-shaped spiller, and the right hand is S-shaped spiller. And the third is radiation. Its definition is scattering of single resonators into periodic arrays, result in appearance of collective interference phenomena not inherent to single resonators. In Lucy's radiation study, Figure C shows the dependence of the radiation Q factor of decay mode in a 1D array of dielectric spheres. One can see that radiation losses disappear only at the certain value of the Bragg wave number, when the decay mode turns into the accidental BIC with non-zero group velocity. The true BIC exists only the infinity long chain when the radiation losses are completely cancelled due to the destructive interference, just in Figure D show. Figure D shows infinity long chain of array, and the last is high Q in BIC. Definition in symmetry protected BIC consisting of several tens of disks behaves as an infinity one, and they find the number of disks are proportional to Q factor, as the Figure F shows. You can see the number of disks is proportional to Q factor. And next is reduced Q factor. High Q resonances in such seemingly different metasurfaces with broken symmetry meta atoms, but it can be unified by the BIC concept. Resonances originate from symmetry protect BIC, transformed into quasi-BICs due to the breaking of the in-plane inversion symmetry. So we put this concept in manipulation, using scattering light in broken symmetry metasurfaces, just as Figure G shows. And the design of the unit cells of asymmetry metasurfaces with a broken in-plane inversion symmetry, as Figure H. And you will find a typical behavior of change of reflectance spectrum from the metasurfaces with symmetry geometric. Alpha equal to 0 is a broken symmetry metasurfaces alpha equal to 0.25 is shown in the figure. So I'll make a short conclusion. Q factor dependence on the asymmetry parameter was analytically and numerically proven for arbitrary metasurfaces with small and moderate degree of asymmetry. And last I will introduce novel concepts for lasing. The abstract is the strong field confinement associated with anodes, and BICS stimulated the design of new types of nano lasers. We try to stimulate emission of amplify an anode state, so we generate a more locked signal in nanowire. Figure A. In INGAS nanodisk is placed in the middle of optical circuit composed of 4 silicon nanowires. And in figure B, by pumping linearly polarized light onto the nanodisk, the enable mode can be selectively excited with the nanodisk. But pumping the scattering mode of the INGAS structure, no couples occurs, shown in figure C. And figure D shows an enable chain of weakly coupled nanodisks generates a model-locked signal propagating in the nanowire channel, and so does figure E and F. Path chains of different period are generated by acting on the chain geometry. And I make a conclusion. Numerical stimulation shows that the enable chain behaves very closely to the optical neural network, opening also future application of enables for optical integrated neuromorphic photonics circuits. Next is BIC for lasing, using the array of connected semiconductor nanodisks shown in figure G. In figure G, with thickness of 300 nanometer and ready vary from 500 to 550 nanometer by decoupling from the radiation continuum, and it is found an optimal radius of 138.4 nanometer for the Q vector, which corresponds to the geometry for which two models close to excitation frequency create BIC states. And here comes the question: how to affect laser's angle and wavelength? And I start in 3 points. First is the geometrical parameters of a lattice. Figure H sketch of the nanoparticle lattice grows on the glass substrate. Second is the peak of gain spectrum of GAS. The third is the temperature range of operation is in this work, limited to 77 to 200 K. And here comes summary and outlook. In the final, I will make a summary, include achievement, high index dielectric resonant structures advance, and future version, as above. We solve enhancement of electromagnetic field by rearrange the array of enable, and study nonlinear and quantum effect in BIC concept, and further improving the value of the Q vector with the help of plasmonic structures, and final confinement of light in high-index dielectric resonators with significant advantage for integrated photonics application. In dielectric resonant structures advantage, we found there are some characteristics such as chip scalability and simple geometrical structure that can be integrated into an on-chip circuitry. So we can find a future version that help to develop of the other approaches for achieving high efficiency in all dielectric resonant optical structures, which has great potential to open a new era for all dielectric metal devices in nano photonics and meta optics. And thank you for your listening.